Welcome to Cyclogenesis, analysis utilizing geostationary satellite imagery. This is a basic session with a slant on utilizing satellite imagery to develop conceptual models which can then be used to improve the forecast from NWP alone. The authors of this session are myself, John Weaver, Dan Vikos, who will be teaching about half this session, Roger Welding from Nesdis in Washington, Toby Carlson from Penn State University, and Dave Valley from the Boston WFO. The objectives of this session are to simply examine various conceptual models of cyclogenesis, starting with the basic cyclogenesis, and then some variations, and then to learn to utilize a blend of the conceptual models and the satellite imagery with numerical model output to diagnose ongoing cyclogenesis. True understanding of cyclogenesis began in the early 20th century with work by the Norwegians. This is from a paper by Bjerknes and Solberg in 1922. Utilizing some fairly shallow, a few thousand feet kite data and a few thousand feet balloon data, they were able to pretty well describe the nature of extratropical cyclones, although they didn't have enough data to develop the understanding of cyclogenesis at the time. Throughout the remainder of the 20th century, meteorologists came to understand that cyclogenesis is a three-dimensional process, which begins when an upper level system overrides some boundary layer features such as a surface trough, a frontal zone, or a low pressure center. The consequence near the surface, the thing that concerns us as forecasters, is the ascending motion, convergence, pressure falls, precipitation, and winds. The first part of the session is going to be review of the basic process, and for this review we're going to be using some diagrams that were supplied by Roger Weldon from NOAA Nesdis in Washington, and we're going to be showing some satellite examples for each case. Cyclogenesis usually is set up when a wide frontal cloud band, high cirrus cloudiness associated with a subtropical jet, is interacted with by with an upper-level disturbance such as a shortwave trough. At the surface, beneath this wide frontal cloud band, we typically have a stationary front separating very warm air to the south and east from cooler air to the north and west. On satellite, this wide frontal cloud band, this is 6.7 micron imagery, and on satellite, this wide frontal cloud band looks like this. We have a high cirrus stream of, high-level stream of cirrus moving up from the subtropics up into the mid-latitudes. We have some embedded jet cores. And we're going to be looking for shortwave troughs approaching this wide frontal cloud band to begin the cyclogenesis process. From a satellite perspective, the cyclogenesis process begins with the Baroclinic Leaf, with the development of what's come to be known as a Baroclinic Leaf. Throughout this session here, we're going to be using terminology that represents a consensus of most of the people that we talked with as we went along developing this session. There's a little bit of differencing in names people call various stages and various features of cyclones. We're going mostly with consensus. In this case, the Baroclinic Leaf phase is used by almost everyone in the field now. Baroclinic Leaf begins to develop as the cyclogenesis begins to develop, and what we see on satellite imagery is the development of a crescent shape in the wide frontal cloud band. Diagrammatically, this is what the setup of the Baroclinic Leaf looks like. A little crescent develops on the wide frontal cloud band as the shortwave moves into the region. We have the jet stream shown here, indicated here. This is the mean position of the jet in most cases, at least 2/3 of the cases to 3/4 of the cases, depending on who you talk with. And this is what that looks like on satellite. We have the wide frontal cloud band here and a little indentation developing, a crescent shape, and maybe some drying here. As substance behind that wave begins to affect the air mass behind the developing cyclone. Many researchers feel that we can use the developing Baroclinic Leaf to identify the incipient position of the surface low. There's a little scheme to develop that, which involves drawing a line perpendicular to the surface frontal zone through the inflection point of the crescent. I'll show that diagrammatically in a minute. This rule represents a consensus amongst about 6 out of 7 research scientists that we talked about on this point. Diagrammatically, here's what that rule looks like. You take a line and draw it through the inflection point on the developing baroclinic leaf, and draw that line perpendicular to the surface frontal zone, or the leading edge of the wide frontal cloud band. And within a degree or two, this is where you're going to find typically find, depending on who you talk to, more than half. Others are saying as much as 3/4 of the time. You'll find a developing low here along the leading edge of that wide frontal cloud band along the surface front. As the surface low begins to deepen and the interaction continues with the upper level shortwave, the cyclone begins to develop some vertical motions. Air from south and east of the surface low begins to be drawn toward the low and then upward through the troposphere, comes up around the north end of the developing low, and then is shunted off when it reaches 500 or 400 millibars to the east by the jet. This is known as the warm conveyor belt. We also have a second conveyor belt that develops north of the surface warm front in the cooler air, and this air is drawn up and around the north side of the developing low, back further to the west in a system relative sense before it too gets shunted off to the east. Here's what the warm and cold conveyor belts look like diagrammatically. Here's the developing surface low right in here. We have the warm air coming up from the warm sector being drawn back toward the low until it gets up to 400 or 500 millibars where it gets blown off toward the east. Also the cold conveyor belt coming in just a little bit below the warm conveyor belt, coming back around that developing surface low, again in a system relative sense, and then finally gets shunted off toward the east at around 600 or 500 millibars. This cold conveyor belt becomes a crucial factor to a satellite meteorologist in that we look for this mid to lower cloud deck pushing out around the developing low to identify an important phase in cyclogenesis. As cyclogenesis continues and the cold conveyor belt begins to emerge from the west side of the developing system, we begin to see a lower cloud deck emerge. And we also begin to see at this point typically a dry slot intrusion as the subsiding air behind the shortwave begins to move down to in from the south and west of the developing low. As the wave deepens, the surface low position, which had been along the leading edge or the eastern edge of the wide frontal cloud band, or what we now call the warm conveyor belt, begins to move poleward relative to the upper cloud deck. Diagrammatically, here's what the advanced leaf phase looks like. The surface low begins to push back toward the western edge of the wide frontal cloud band, which is now typically called the warm conveyor belt since the cloudiness now represents low-level air which is being brought up in the troposphere and up into the system and then vected out to the east. This low-pressure system will continue to move back toward the eastern edge of the cloud band as the system deepens. It's long about this time on satellite imagery when we begin to see a lower cloud deck begin to push out to the west here and the cold conveyor belt reveals itself. This is typically a sign that the cyclogenesis is going to continue. This is what it looks like on satellite imagery. We've got the large crescent developing here. We've got a fairly substantial dry slot that's developing, and this is the area right here where we're going to be looking for that cold conveyor belt to push out. Along about this phase, the surface low is typically somewhere near the middle of that warm conveyor belt. Finally, as the system reaches maturity, we evolve to what's come to be known as the comma shape. We have the cold conveyor belt pushes out to the west of the system, and the dry air begins to nip off the edge of that cold conveyor belt, resulting in a cusp shape on the west of the system, to the west of the system in a system relative sense. Diagrammatically then, this is what that looks like. We now have the cold conveyor belt pushing out back here. The subsiding dry air has nipped off the edge of the cloudiness associated with the cold conveyor belt, making a little cusp shape to the west of the low. The low pressure system at this point is pushed to within a degree or two plus or minus of the edge of the warm conveyor belt here. The surface low will either be just west of by about a degree or just east of, just slightly east of the western edge of the warm conveyor belt. And the surface low at this point, just as the cusp develops, will be due east of that cusp. That's an important principle because you can use that in areas where we don't have much data to check how the models are doing. On the satellite, this is what that looks like. Here we have the Here we have the crescent that we've been watching. Now we have these slightly warmer clouds that pushed out behind the warm conveyor belt. The dry air has come in here and nipped off the edge of that cold conveyor belt cloudiness, formed the cusp that we're looking for, and the surface low at this point is going to be somewhere in this vicinity, plus or minus a little bit. So the takeaway points here for the conceptual model discussion is that we want to look for the development of the Baroclinic Leaf, realizing that the surface low is out here somewhere near the eastern edge of the wide frontal cloud band. We want to look for the appearance of the cold conveyor belt. Sometimes, depending on the color table that you're using, it may be a little hard to see, but when you're looking for it in a loop, you can clearly see it. At this point, the low is beginning to move back toward the western edge of the warm conveyor belt. And then finally, we want to look for the development of a cusp, because once that cusp develops, we know that the low is very near the western edge of the warm conveyor belt. And we will be able to use this cusp through the next phases of the basic cyclogenesis to track where that surface low is going to be in a system relative sense. Finally, as the system reaches maturity, that cusp begins to wrap around the system, again in a system relative sense, begins to wrap around the low. Here, as the cusp starts to head eastward, the low begins to rotate around that cusp, very near the western edge, or very near the cool edge of the warm conveyor belt. And as time progresses and the system begins to occlude, we'll find that this low continues to spiral around that cusp until it gets into the middle of the system here, when we have the system beginning to fill in. On satellite, this is what that looks like. The cusp is now kind of pointed off toward the east here. The low is going to be to the northeast of that cusp at this point, and it's going to be, in a system relative sense, continuing to rotate around the cusp as the cusp heads eastward. And the final stage in the cyclone's life is the occlusion process. When the warm and cold air begin to mix, we lose the baroclinic energy. The short wave moves off to the east. The surface pressure begins to rise, and the cyclone is basically in its death throes. So wrapping it up here from a page from Bader's book, want to remember we're looking for this wide frontal cloud band aloft, especially on the 6.7 micron imagery associated with the subtropical jet. Want to look for approaching short waves. Want to look for some interaction happening and a baroclinic leaf developing. This now becomes the warm conveyor belt as warm air is ejected up into the system. And finally, when the cyclogenesis process is completely underway, we begin to see the cold conveyor belt emerge from beneath those upper clouds. This is the first minor case study or an example from the session. We typically ask the class to identify the wide frontal cloud band associated with the upper jet. Most people get the idea that this is the feature that we're looking for. We ask if there's any embedded jets, and most typically point out exactly what we're looking for. Let's go to the middle of the loop here. At the wide frontal cloud band here, we've got an embedded jet here, and then we ask if there is if they can see any upper level system approaching from the west that could possibly be a factor in cyclogenesis later. And most forecasters identify this feature back here as approaching the wide frontal cloud band and perhaps bringing about some cyclogenesis within the next day or so. Here's 300 millibar isotaxon winds for this case. We'll walk through the loop a little bit here. We see the wide frontal cloud band, the jet with a nice embedded jet core right here. Back to the west, we see this approaching shortwave trough and little jet max associated with it. Let me step through the loop slowly and watch the progression of the systems as time passes here through this loop. The area that you want to be particularly watchful of is the place where these two jets phase, where the upward motion portion of this jet phases with the upward motion portion of this jet. In other words, the area between the two jets. We want to look for some enhancement in the water vapor imagery indicating lift, and down here to the south we want to look for a little subsidence. But generally, the approaching wave, the coupling of the jets, the diffluence here that's associated with this wind flow, all combine to help with the cyclogenesis process. And as we continue through the data here, we see that we are now beginning to develop a little distortion in that wide frontal cloud band, although I don't believe cyclogenesis has actually begun yet. This is the next loop in the series from this example, and we can see that the shortwave is now interacting very well with the wide frontal cloud band, and you can see when the cyclogenesis begins. Clearly, I'm going to stop the loop, and we're going to walk through it just a little bit. Erase that arrow. And as this shortwave begins to move in and affect this wide frontal cloud band, I want you to watch for that developing crescent shape, the Baroclinic Leaf. There it is, and soon you will see emerging from that crescent a lower level cloud deck. Right here you can begin to see hints of it. A little hard to see, it's a little easier to see in the loop, but we begin to see some emerging lower level clouds, and finally as time progresses here we begin to see the formation of this cusp in that cold conveyor belt cloud deck there, indicating that now the surface low has reached near the eastern edge of near the western edge of that upper cloud deck, probably sitting right around here. And as we go through time, we can see now the cusp beginning to wrap back to the east in a system relative sense, and this is the time when that surface low begins to wrap back around the system. And I'll animate this again and let you watch that. And now we have the occlusion process beginning as the cloudiness associated with that cusp begins to spiral in and fill in the center of the cyclone. Now, one way that we can use the satellite data in conjunction with the conceptual models that we've been describing is to check how well the models are doing, the NWP models are doing. This example was chosen because it's out over the Pacific where actual data is sparse. And what we're showing here is in cyan, we've got the 500 millibar height field, and in this yellowish-green color here, we've got MSLP, mean sea level pressure. And as we step through the loop, we're going to try to assess how well we think the AVN model in this case is doing. Here we've got that cusp. This is IR channel 4 data underlaying these data, these fields. And we've got this developing cusp, and lo and behold, the model data seems to have a pretty good handle on it. The low is right at the western edge of the upper level cloud deck, and it's due east of that cusp. But look back here, the short wave to the west of the main system is actually undergoing a little cyclogenesis of its own, probably due to some cold air destabilization back there in the cool sector. And yet the model data hasn't picked up a low associated with this system, which is already wrapping up and producing a cusp shape. The reason for that, probably the sparse data. It's a small system, and it's wrapping up fairly quickly, so the model's probably running a little bit behind. As we continue to step through the loop here, we see that the model now picks up a low, but the low is way too far north of where it would really be. Meanwhile, the system here on the east, the model seems to be doing a little bit better job of that. We see the low now beginning to wrap around the cusp in a system relative sense, and as the occlusion process takes place, we begin to see the low fill with pressure. Meanwhile, back here, the model's not doing so well with this small wave here that's developed back in the cool sector. And we'll just go through the occlusion process. And again, watch the way that especially the small cyclone back in the cool sector, how poorly the model does on that. This can help you identify surface low positions, maybe adjust your forecast slightly in terms of location and intensity. But the eastern system is handled quite well. Just for interest, we'll wrap up this case here by showing a day's worth of visible data through this process, and we see here the free cumulus out in the warm sector ahead of the developing big cyclone. Behind that cyclone, we see some cellular cumulus associated with more stable air or cooler air, and back here, the fact that this short wave is now wrapping up into a cyclone of its own. So in summary here, remember that cyclogenesis is a three-dimensional process. The process always begins when an upper-level system of shortwave trough, little jet streak, interacts with something near the surface, preferably a stationary front associated with that wide frontal cloud band. Best way to look at this process is with a combination of water vapor imagery, utilizing the conceptual models to understand what's going on, and then comparing that with the NWP output. Now at this point I'm going to turn it over to Dan Bykos, who's going to talk about some variations from this basic process, showing the similarities and differences, and then we will later in the session apply these principles to case studies.
John just looked at the basic type of cyclogenesis, and now we're going to look at different variations in cyclogenesis. There's many different types of variations in cyclogenesis, but we're going to break those down into two broad categories here. The first, where development occurs at the warm conveyor belt, and the second, where development occurs behind the warm conveyor belt. Here's the types that we'll look at here, and if you're familiar with the terminology that Bader uses, that's what we provided here in the parentheses. The first type we'll look at is the so-called split flow with basic cyclogenesis. And what we have is a jet to the north and another one to the south. We get a cyclone developed to the south here, but that low tends to become cut off and the surface low phase is short-lived. On the northern branch here, we tend to get a basic type of cyclogenesis. Here's our example imagery for our split flow with basic cyclogenesis. Here's the familiar warm conveyor belt that John had been talking about, and you can see some drying occurring just west of that. Another thing that catches our attention here is another system upstream. And what we'll do on the next slide here is just look a little further west using the GMS satellite. Here's the GMS Japanese satellite with the system that we're looking at to the west. Here's the warm conveyor belt that we had just been looking at. And you can see that system to the west has a jet streak associated with it. Recall earlier, John was saying how you need to look in between these two jets here for the development of cyclogenesis. So we're going to keep an eye on this diffluent region right in here. Now we'll go back to the GOES 10 perspective, and in this loop right here we see this jet associated with this warm conveyor belt, and that next system to the west here we see this jet streak right here in the 300 millibar isotax from the AVN analysis here. And again, we want to keep our eye on this region between the two jets, this diffluent region right here. Now at this point I'm going to ask a question: which location is most likely to develop cyclogenesis that will affect the northwest coastal regions of the U.S., A, B, or C? And what we did here was just overlay the water vapor imagery with the 300 millibar analysis from the AVN alongside just the water vapor imagery. If you want to take a minute to respond to that, you can go ahead and hit the pause button. Turns out the answer here is C, and with the next few slides we'll look at exactly what happened. Here's the IR imagery overlaid with MSLP in yellow and 500 millibar heights in cyan. And as I step through this, I want to draw your attention first to this cyclone that develops on the southern end of this system down here. And if we look at the end of this loop right here, we see this southern cyclone right here, and then we see a Baroclinic Leaf up here. Here's the water vapor imagery at that same time, and again you see that low develop to the south here, and we probably expect that to be short-lived because it's cut off from the colder air to the north up here by this other jet. And I want to draw your attention to this Baroclinic Leaf to the north here. So what I'm going to do is stop the loop, go to the end of it here, and point out this Baroclinic Leaf. Now remember, we saw drying occurring west of this warm conveyor belt. It's the first sign you look at for potential for cyclogenesis. The next thing you look at is consider where the inflection point is. And I'm just going to draw it in right there. Use a line instead. And that inflection point is kind of important because south of that inflection point we see this drying occurring. If it was to the north, the cyclogenesis would be less likely to occur. But when we see it to the south like that, that's another sign that that cyclogenesis is more likely to occur. Now let's go on to the water vapor imagery at the next time period here. And again, we see this low to the south here, and it kind of drifts towards the southwest. So clearly that's not the low that's going to impact the U.S. And to the north here, we see this basic cyclogenesis result, and it does indeed impact the coastal regions of the northwest U.S. What I'm going to do is stop the loop and go to the time just before it develops. And I want to draw your attention to this region south of the inflection point in this drying region here, just west of the warm conveyor belt. And notice at this time right here, we start to see yet another change in curvature, or a kink, just east of the drying here. And that's kind of the final sign that we've seen in the buildup of all these factors that lead you to believe that cyclogenesis is more and more probable to occur. And once we see that little kink or change in curvature occurring just east of that drying, soon thereafter is when the basic type of cyclogenesis results here. Another type of cyclogenesis is the so-called cold air cyclogenesis. This starts out with an upper level shortwave moving towards a warm conveyor belt. But what happens is we start to see cyclogenesis result west of this warm conveyor belt here. So the one thing that this is characterized by is development occurring west of the warm conveyor belt. So we see this spacing in between the warm conveyor belt and where this cyclone is developing. There's no cold conveyor belt in this case, therefore there's no warm frontal zone with the new cyclone. Typically these are not as intense as the others because we're not drawing into the warmer, unstable air east of the warm conveyor belt here. And what's going on here is this is developing because this short wave is interacting with an area that's generally very cold aloft, and therefore you have very deep or steep lapse rates. Now let's look at the 300 millibar analysis from the AVN overlaid with the water vapor imagery. You can see this trough in the Gulf of Alaska with a jet streak to the east associated with this warm conveyor belt. And you can see another jet to the west of this trough right here. And that's going to play a role in this cold air cyclogenesis that results here in the Gulf of Alaska. Now let's just look at the water vapor imagery by itself. Again, here's the warm conveyor belt, and here's the cold air cyclogenesis that's occurring here, west of the warm conveyor belt, and you can see this cumulus look to the clouds right here, indicating the very steep lapse rates or very cold temperatures aloft. Now let's analyze how this event was handled by the AVN analyses here. And what I'm going to do is just step through the loop here. And you can see by this time right here, it looks like we already have a low developing. However, in the model analysis, the MSLP here in yellow, we don't see a closed low yet. And in fact, we don't see a closed low develop until this time right here, where we clearly had a low by this time, but the model is definitely slow to pick it up. Of course, we have a lack of surface observations out here over water, and we heard from some of the West Coast offices that the models tend to struggle in terms of picking this up in time. In other words, the models tend to pick this up a little too late because of the lack of surface observations. So what you can do is when you see this type of pattern, where you have a warm conveyor belt and you see a jet impinging on an area of cold air aloft, and you see this type of development occurring, you can anticipate this type of cyclogenesis better than the models alone. Our next type of cyclogenesis is the so-called instant occlusion cyclogenesis. It starts off looking a lot like cold air cyclogenesis, where we have an impinging short wave moving towards this warm conveyor belt. But once again, just like in cold air cyclogenesis, we see the cyclone develop west of this warm conveyor belt right here. So early on, we see this space in between the warm conveyor belt and this developing low. However, what happens next makes it different from cold air cyclogenesis. What we see is so-called secondary warm conveyor belt develop right here. And once that develops, the warm, unstable air is able to tap into this upper level low to the west here, and when that happens, we get a low developed right in here, and that tends to develop quite rapidly. I just mentioned the secondary warm conveyor belt, so I thought I would spend a minute going into some detail about this. It was introduced by Young et al. In 1987, and it's depicted right here, and what happens is it kind of peels off from the warm conveyor belt and develops out in this region right here. The ageostrophic transverse circulation at the jet exit region is important in generating the secondary warm conveyor belt. And of course, having instability in this region is important as well. Let's go to our example imagery now. And we can see the warm conveyor belt right here off the Atlantic coast. And we also see this low, or upper level shortwave here to the west. And at least early on, we can see clearly some spacing in between the warm conveyor belt here and this upper low or shortwave to the west. But then what happens if we go to the end of the loop here is we see convection start to fill in right here between the warm conveyor belt and this upper level system to the west. And when that convection develops in this region here, we develop that secondary warm conveyor belt, and therefore that warm unstable air is able to wrap around all the way back to this region here and develop this low off the coast. Sometimes this can be seen more easily in the IR imagery, so we'll look at the IR loop here. And let me just go to the time period here where it's pretty clear we have a warm conveyor belt here, and we have this upper level shortwave to the west, and we have nothing occurring in between the two. So at this point it looks like cold air cyclogenesis. But then as we advance through time here and we get to this period right here, we see convection fill in between the warm conveyor belt and the upper level system to the west here. And that's a sign that that secondary warm conveyor belt has developed. We're able to transport that more unstable air to the west here, and the result is a rapid fall in the pressures right here. The next type of cyclogenesis we'll look at is the so-called in-stream cyclogenesis. This is characterized by a zonal or quasi-zonal warm conveyor belt, strong flow with embedded shortwaves, and the result is a family of cyclones. Here's our example imagery for the in-stream cyclogenesis case. Here's our warm conveyor belt, approximately zonal, and what we get is a number of different cyclones developing just north of this warm conveyor belt. So if we go to the start of the loop here, we can see the first cyclone right here, and then if we advance a little further on, we see another cyclone right here, and then we see another one develop right here. So that's why we call it the family of cyclones here, where we just keep getting a number of new cyclones developing just north of this jet. Now let's analyze how the models did with this particular case by looking at each of these cyclones individually. This first one right here looks like it did at least a fairly good job in the position of the low. The next one over here, it looks like it did a reasonable job, probably not as good. I can see a little bit of difference here, but still a reasonable job in terms of depicting the location of the low. But more interesting is this new low that develops out here. Now let me advance to the time that it develops right here. And by this time right here, you can definitely tell there's a low. Here's the cusp. Here's the coal conveyor belt coming out. However, in the MSLP, we do not have a closed low as of yet. We just have a trough. And in fact, the models did not have a closed low until about this time right here, where it was clear a few frames earlier. We definitely had a low in here. And we talked to some of the West Coast forecasters in our testing phase of this session, and they told us that this type of pattern that models tend to struggle in terms of picking up on these lows. Of course, you have a lack of surface observations out here. But the point is, when you see this type of pattern, you can anticipate this type of cyclogenesis a little better now, certainly better than the models. Next thing we're going to do is look at two case studies John will look at a nor'easter case from 24 February 1999, and I'll look at a leaf cyclogenesis case from 11 April 2001. Our purpose is to utilize different data sets, apply QG theory along with the conceptual models that we've been talking about today, and use a blend of various inputs to forecast location and intensity of cyclogenesis. So with that, I'll turn it over to John for the first case.
Okay, this case will be for the Boston CWA. We'll be looking at a wintertime nor'easter. This is the Boston CWA portrayed here, and the case will be the 24th of February, 1999. This case begins with an overview of the maps from the morning of, from 12Z on the 24th of February, 1999 during the live teletraining session. I use these maps as an overview of the situation. We'll be forecasting for the next day, 25th of February. This is going to be the long-range forecast for the morning of the 25th of February. What we're looking at here is the 300 millibar heights and ice attacks. The 0-0 analysis at 12Z on the 24th. We see a broad trough over the eastern United States. A little bit of a disturbance here coming through North Carolina, Virginia area. And as we step forward 6 hours to 18Z, we can see that this feature continues to progress eastward throughout most of the day on the 24th. And as we get into the late evening hours of the 24th at 06Z on the 25th, we see jet minimum right here near the center of this little trough that's coming through here. There's got to be a lot of diffluence associated with that. And finally, we get into toward the time of the forecast period. The trough is just off the coast. A couple hundred miles off the coast, it looks like, well off the Jersey coast, to the south and east of our forecast area, which remember is right here. And finally, midday on the 25th, we're looking at that trough moving off toward the northeast in the direction of Nova Scotia. Here's the 500 millibar heights and vorticity from the ADA analysis, again beginning at 12Z on the 24th and going up to the period that we're going to be forecasting for. We see again this trough moving through Virginia and North Carolina here at 500 millibars. I typically show this vorticity analysis embedded here to accent the fact that during strong flow situations such as midwinter, in this case, vorticity gets kind of confusing because we're looking both at circulations and at shears, and so we have a lot of vorticity maxima embedded here, and it's not really the best way to look at the situation for developing cyclones. Nevertheless, we'll step through the data, and we'll go to the first 6 hour period, which is 18Z. Watch again this trough with a little vortmax as it moves off coast here, moves off the Virginia coast, begins to move northeastward. And we finally get a 500 millibar low at 12Z, which is the time we're going to be forecasting for, well off the coast over south and east of our forecast area. And remember that the surface pressure is probably going to be somewhere a little bit east of this 500 millibar low in a developing situation. And finally, at 18Z on the 25th, the low deepens even further and continues to move off toward the northeast. Before we go too far looking at the model data, we want to maybe put the 6.7 micron water vapor loop up for the period approaching our forecast time. And in this case, we're running this loop from 0Z on the 24th all the way up through 13Z on the morning of the 24th. Keep in mind that we'll be forecasting for the next day. I'm going to stop the loop here and identify some features that we've been talking about during this course, the conceptual models that we've developed. Here's that wide frontal cloud band that we talked about coming up through Florida and then off the coast of the United States. Keep in mind that the warmer air is here and the cooler air is back in this sector here. Keep your eye on this short wave that we've identified on the models. It looks a lot clearer on the satellite imagery than it does on the 500 millibar analysis. Although the ADA and also the AVN in this case handle its positioning fairly well. Let's step through this loop just a little bit. And we'll watch this short wave as we approach the forecast time, which is the morning of the 24th, the time we're getting ready to prepare the forecast for the next day. We see this system moving through the Carolinas here toward the end of the loop. And at this point in the live session, I always ask the forecasters to first identify some of the features that we do talk about, hoping that they'll pick up this wide frontal cloud band. And also I ask if there are any features that affect the East Coast, any special features that affect the East Coast, particularly for the potential development of cyclones in the wintertime. And we always get the proper answer, which is we have a good heat source here, good low-level heat source with the Gulf Stream as it comes up along the east coast of the United States. So when this, what is basically here, cold air cyclone or shortwave that's coming through the Carolinas and Virginia hits that Gulf Stream, we can expect some intensification here. We'll also be looking for the possibility of intensification if this cold air cyclone begins to merge with and occlude with the warm conveyor belt here, or rather the wide frontal cloud band here. Okay, let me run that loop just a little bit more, and we can see now toward the end of that loop that we're beginning to get out over the Gulf Stream, and we're beginning to develop some small convection here. We want to look now at some of the surface variables. I want to look at the mean sea level pressure forecast from the ADA model again. Look at the forecast precipitation and the surface wind field for the up through the period that we're going to be forecasting for. We notice, I'm going to animate the loop here and just watch how the surface low moves. The surface low basically moves up toward the northeast, heading for Nova Scotia. And if you'll notice, the precipitation field kind of skims the Boston CWA, the area that we're going to be forecasting for. I'll stop that, go to the end of this loop, and you'll notice that the low pressure at this time at 18Z on the 25th is well off coast, and the edge of the precipitation field is hitting the Boston CWA with what looks to be about, say 0.03 to 0.05 inches of liquid precipitation. If we go back here, we see about the same amount over this 6-hour period. Go back here, we get just a trace in there. So for the forecast period, which runs from, say, 6Z, let's call it 6Z through 18Z, that 12-hour period there, we get, through that 12-hour period, we get a trace, we get 3, and we get 3 again. So we may have as much as 0.12 to 0.15 liquid, converting that at 10-to-1 ratio. We're looking at maybe an inch or two of snowfall for the Boston CWA during the rush hour on the morning of Thursday, 25 February 1999. At this point now, we're going to keep this forecast in mind, and keep also in mind the very rapid increase as we approach the system center here of precip. We get periods here where we get upwards of 2 inches of liquid precip offshore, just a little ways offshore. That's one of the things that the East Coast forecasters are always leery of, is what happens if this low goes just a little bit further west than it's forecast to go. Okay, now we look at the next 6.7 micron water vapor loop, which runs from forecast time 14Z on the 24th up through late on the day on the 24th, 02Z on 25th of February. And a couple of the things we try to get the class to notice during this portion here, let me stop the loop, is that as that cold air cyclone begins to move out over the Gulf, we begin to develop some very deep convection, and indeed radar data showed some very intense echoes here just off the coast. But we also want people to notice that convection toward the end of this loop is beginning to develop between the cold air cyclone and the warm frontal cloud band here, indicating the possibility of instant occlusion and drawing some of that very warm air from the warm sector of the Atlantic. Second point we try to get people to notice is, or the question that we ask is, where do they think the surface low is based on this satellite loop here? And what we hope that they notice is that using the conceptual model that we've been talking about here, at this point we've got this little cusp developing. The low is over here somewhere. Let me just put a little circle where the low is, and as we continue through the loop with time, we begin to see now the cusp wrapping around the system. So the low is beginning to move up around the system in a system relative sense, and as the loop continues here, the surface low would now be beginning to curve back toward the north. And indeed, at this time, let me erase the guesses for that surface low position and just animate the loop and ask you to notice that the surface low, in fact, the system itself seems to be moving almost due north instead of northeasterly as earlier expected. If this is the case, remembering back to that ADA MSLP forecast, we can very quickly get into the area where we're talking about 1 and 2 inches of liquid precip every 6 hours or so. And if we get that much, say we get even 2 inches of precip, we can get upwards of 10 to 20 inches of snowfall. So just based on this loop alone, for the evening update for the next morning, our suggestion is that the satellite information be utilized to not necessarily make a quantitative precipitation forecast, but maybe nudge the forecast amounts up just a little bit. Most forecasters reach the consensus here that we should nudge up from around 2 to 3 inches, maybe up to 8 or 10 inches for that morning rush hour. Better safe than sorry, particularly with that embedded convection that's on the eastern edge and wrapping around the cyclone from the east. Here's a quick comparison of where the conceptual model and satellite imagery would place the low versus where the low was analyzed or forecast on the evening ADA run. And this low on the ADA was moving up this way using the satellite data and actual surface observations nearby. We find that this low actually moves up in this direction here, bringing in considerable amount more precipitation to the Boston area than would have been expected either on the previous morning's ADA run or on the evening's ADA run. Finally, here's the snowfall totals for the period 06 to 18Z, for actually the storm total, which represents the period 06 to about 20Z. We got in some areas nearly 20 inches of snow. Most of the areas had at least a foot. As that low brushed the Cape here, brushed much closer to the Cape than was originally forecast. The Boston CWA helped us a lot with this case. They told us that they recognized the fact that the low was moving more northerly than northeasterly, and did bump their totals up overnight to reflect this closer approach of the cyclone, and were able to get a pretty accurate forecast for the morning rush hour. So in summary, the 24th of February nor'easter case sort of began as cold air cyclogenesis, the little wave back to the west over Virginia and North Carolina. Sea surface temperature gradient always plays a role on the East Coast, and that took that short wave to a new level. And then the cyclogenesis finally transitioned to instant occlusion and began to draw warm air from the warm sector east of the wide frontal cloud band overnight. The ADA seemed to be playing catch-up and was too slow, but utilizing the conceptual models of satellite imagery to nudge our NWP output just a little bit, we're able to get a better handle on where that heaviest snowfall is going to be. So at this point, I'm going to turn it over to Dan Bykos for the last case in the course.
Now let's look at a case study from 10/11 April 2001, and we'll be considering the Goodland, Kansas CWA here. We'll set this case up with looking at the progs. First, we'll look at upper levels. Here's the ADA forecast 500 millibar heights with vorticity shaded. And you can see a four corners low prog to move towards the northeast into the plains and deepen. At low levels, here's the 850 millibar analysis. We see a pretty good warm advection pattern through the southern plains. And keep in mind, this is springtime, early April, so that, of course, means we're advecting in a fairly unstable air mass ahead of this low-pressure system here. And you can see a pretty good warm front up into Nebraska and Kansas here as well. And as we advance through time, you can see this low is forecast to move towards the northeast. Here's the water vapor imagery. First thing you'll notice here is the warm conveyor belt. Second thing you'll notice is this upper level low over Colorado here, and we see space in between the two. Now recall, this is cold air cyclogenesis, and the next thing you would be looking for is, you would ask yourself the question, is this going to evolve into an instant occlusion type of cyclogenesis? And the thing you would look for is convection developing between the warm conveyor belt and this upper level low. And the things you would need to assist yourself in terms of that forecast is assessing the instability in between the warm conveyor belt and this upper low, and also keeping in mind where the position of the jet max is as well. Recall that the ageostrophic transverse circulation in the exit region of the jet was important in generating the secondary warm conveyor belt, as well as low-level instability. Well, I showed earlier in the 850 millibar analysis we had a pretty good warm advection pattern, so we have pretty good instability. It's early spring through this region in here. And now if we look at the 300 millibar analysis here with the 300 millibar heights and isotax here in the dashed yellow, we see that the jet max here in northwest Oklahoma Panhandle puts this region right here in the exit region of the jet. So it looks like we have the favorable conditions here for a secondary warm conveyor belt to develop in this region, and therefore convection to develop here. Let's go to the water vapor loop over the next time period here, and we see this convection does indeed develop between the warm conveyor belt and the upper low over Colorado. Let me go advance here to 6Z, and you can see the convection is pretty well filled in between the warm conveyor belt and this upper low. And what that indicates is that we have that secondary warm conveyor belt feeding that warm, moist air into the upper low back here, and the result is pretty rapid pressure fall starting around 6Z. And if we just look at this imagery here, we look at the position of the cusp right here, and since we're fairly early in the development of this low, we would put the surface low just east of that cusp. Therefore, the surface low we would expect to find somewhere in eastern Colorado. Keep all this in mind as we look at the next slide and we go ahead and look at the MSAS analysis of MSLP. Now let's look at the MSAS MSLP analyses here. Two things we want to look at. First, the position of the low, and also we'll look at when the pressure started to fall most rapidly. Recall the position of the low around 6Z that I just drew in based on the satellite imagery was somewhere in eastern Colorado. And we see in the analyses here that it analyzed the low somewhere in southeast Colorado, a little bit further south. And a couple reasons for that, I guess you can call it difference between the positions of the low based on the satellite imagery in this analysis here. First would be that we have a leaf cyclogenesis case where the stretching of vorticity is pretty important in terms of the change in terrain from the higher elevation here to the lower elevation. And that stretching vorticity, of course, causes the leaf cyclogenesis to develop here. Another factor that's involved here is also the influence of downslope winds and changing where the warm advection is going to be in this region here, and that will have an effect on where that surface low placement is as well. Now, another thing to consider here was, recall, based on the imagery, we saw that secondary warm conveyor belt really start to develop around 6Z, and therefore we would expect the pressure falls to start most rapidly around that period. So let's verify that and look at the pressures. At 1Z it was approximately 990, and at 2Z about 990, holding steady. 988 at 3Z, 989 at 4Z, hasn't really started to fall quite yet. At 5Z it's 989. Then we jump ahead to 7Z and it's dropped to 985 millibars. And then at 8Z down to 983. And then by 10Z it drops considerably down to 980 millibars. So indeed, right around 6 to 7Z we started to see those pressure falls most rapidly. And that was in response to that secondary warm conveyor belt developing, which allowed the warm unstable air mass here to feed back to the west towards that upper low and really develop that surface low pressure here. Now let's summarize this case. Satellite imagery showed instant inclusion cyclogenesis in the lee of the Rockies. Initially, we had a well-defined warm conveyor belt with an intense shortwave to the west and cold air cyclogenesis over Colorado. But then what happened is we saw convection associated with the intensifying cyclone merge with the warm conveyor belt. So we saw that secondary warm conveyor belt develop. And when that happened, we saw a rapid deepening of the low, and that, of course, meant that we had instant occlusion cyclogenesis taking place. The most comprehensive overview of this case was made possible by the use of conceptual models that we looked at in this session here, NWP analyses, and satellite imagery, all combined here. Now let's summarize the whole session. We reviewed the process of cyclogenesis. We reviewed the components of the flow. We learned that cyclogenesis can best be diagnosed using a blend of satellite conceptual models and NWP. A combination of satellite imagery, conceptual models, and NWP analyses outperforms the use of NWP alone in the short-range forecast. And here's an important takeaway point. The names of the variations in cyclogenesis types should not be the primary focus. In other words, we don't need you to memorize all the names of the types of cyclogenesis we covered. What's important is the physical processes. So if you know the physical processes, you'll be able to kind of recognize the pattern that you're in, and remember the different conceptual models that we looked at here. And from that, using that knowledge of the physical processes that are going on with the satellite imagery and then the NWP, you can outperform the models here. And that's the whole goal.